Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
Singlet fission, SF, is a process in which an organic chromophore, a molecule that absorbs light, in an excited singlet state transfers energy to a neighboring chromophore, resulting in two correlated triplet exciton pairs, pairs of bound electron-hole states, a hole signifying the absence of an E. These excitons have long lifetimes and show efficient light emission, making SF promising for efficient light energy conversion. However, the molecular design of SF-based materials is limited by the requirement that the energy of the excited singlet state must be at least equal to the energy of the two triplet states. One way to overcome this limit is by applying external stimuli, such as temperature or pressure, to manipulate the SF process. Now, in a collaborative study published in the journal Chemical Science, Professor Gaku Fukuhara of Tokyo Institute of Technology, Tokyo Tech, and Professor Taku Heisobe of Keio University in Japan demonstrate, for the first time, a hydrostatic pressure-based strategy for controlling the dynamics of the SFP. We demonstrated hydrostatic pressure-controlled formation and dissociation of correlated triplet pairs in SF by means of pressure-dependent UV/vis and fluorescence spectrometry along with fluorescence lifetime and nanosecond transient absorption measurements, explained Professor Fukuhara and Professor Heisobe. In their study, the researchers used a biphenyl-bridged pentacene dimer as the model chromophore and tested its response for a range of hydrostatic pressures, from 0.1 MPa, atmospheric pressure, to 180 MPa, in three different solvents, toluene, methylcyclohexane and tetrahydrofuran. Using a custom-built high-pressure apparatus, the researchers measured the rate of exciton generation at different pressures by monitoring the fluorescence lifetime decay of the chromophore, which indicates how long the chromophore takes to emit a photon after the initial excitation. They found that the rate constant for the generation of correlated triplet exciton pairs increased with pressure, indicating that higher pressure leads to a faster SF process. Using the technique of nanosecond transient absorption, the researchers then tracked the decay of the triplet excitons and found them to have shortened lifetimes under high pressure. Based on quantum yield calculation and thermodynamic estimations, the researchers uncovered two mechanisms underlying the generating correlated pairs and individual excitons. In the case of the correlated exciton pairs, the SF process was driven by the solvation and desolvation of the molecule, leading to a more compact and thermodynamically stable exciton structure than the excited chromophore. In contrast, the individual excitons produced by the dissociation process were found to be thermodynamically bulkier, causing the solvent molecules to cluster around and deactivate them at high pressures. With these findings, the researchers have shed light on the interactions between the different systems, pressure, solvent, chromophore, excitons, involved in the SF process, suggesting a suitable alternative to the conventional control strategy for SF. Our study provides a new perspective on the control of intramolecular SF using hydrostatic pressure as an external stimulus. This dynamic control concept could be extended to other SF scaffolds and relevant systems that are difficult to control in both ground and excited states, speculate Professor Fukuhara and Professor Heisobe. We can certainly hope to see the application of SF-based materials in the design of efficient organic solar cells and photoconversion devices. Thanks for watching. Please subscribe my channel for more videos.